Let's test your knowledge of cyclohexane conformations. Which conformation of cyclohexane is the most stable? Half chair, boat, twist boat, or chair? Lock in your choice. We'll reveal it in a moment. In this video, you'll learn how cyclohexane really sits in 3 dimensions, why the chair conformation is so stable, how to label axial and equatorial positions, and how ring flips swap them. First, a reality check. We often draw rings from the top down, but cyclohexane is not flat. Rotation around bonds is limited because the ring must stay closed. That pushes the molecule into specific shapes. Now, back to the question earlier. The most stable shape is the chair. It wins for 2 big reasons. First, every carbon sits close to a perfect tetrahedral angle, about 109.5 degrees, so there is minimal angle strain. Second, if you check any carbon-carbon bond with a Newman view, you find staggered bonds all around the ring, which reduces torsional strain. To read the chair, picture each carbon as a little pyramid, with one bond leaning toward you and one away. Keep that depth in mind. This side is nearer, that side is farther. When you see the chair edge on, the 3-dimensional angles stop looking random. Let's add hydrogen positions. Start with axial bonds. They alternate up, down, around the ring. Axial means roughly parallel to the ring's vertical axis. Next, add equatorial bonds. These slant out around the rim. Axial and equatorial alternate at every carbon, and together they account for the full tetrahedral geometry. Let's zoom in. At carbon 1, the axial bond points up and equatorial bond points slightly down. At carbon 2, they swap directions. This alternating pattern repeats around the ring and keeps the strain low. Watch out for 3 pitfalls. 1. Do not flatten the chair into a lightning bolt line. 2. Avoid perfectly vertical lines when sketching because they hide depth cues. 3. Label axial and equatorial carefully because they alternate. Mini checkpoint. You can now recognize the chair, explain why it is stable, and place axial and equatorial bonds correctly. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Let's flip the ring. Cyclohexane can invert from one chair to the other. During a ring flip, every axial position becomes equatorial and every equatorial becomes axial. For plain cyclohexane, both chairs have the same energy. Now, let's add a group. With methyl cyclohexane, the equatorial chair is favored. The reason is axial methyl crowds the ring through 1,3 diaxial interactions, so the molecule prefers to flip into the chair, where the methyl is equatorial and farther from those neighbors. What about the other shapes? The boat puts several bonds in an ellipsed arrangement and squeezes 2 hydrogens together at the bow and stern. Twisting the boat eases things slightly, but neither matches the chair's low strain. Let's practice drawing. Start by sketching 1 pair of parallel lines. Then add another pair slightly offset to form the top and bottom edges. Connect the tips to create a clean chair shape. Add alternating axial bonds up and down, then draw the equatorial bonds in alternating directions. Finally, label 1 carbon to track its position during a chair flip. Recap. The chair minimizes strain with near tetrahedral angles and staggered bonds. Axial and equatorial bonds alternate at every carbon. A ring flip swaps them, and substituents prefer equatorial positions to reduce crowding. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.